Welcome back to the course on signal processing for music applications. In this week that we're talking about the sinusoidal model, in the programming lectures we have been trying to put together a whole system for analyzing and synthesizing a sound using this sinusoidal model. So in the first programming lecture we talked about the peak detection, how to detect the peaks of a spectrum, which hopefully are going to be sinusoids. Then in the last programming lecture, we talked about how to synthesize sinusoids from those values, from the peak values. And now in this lecture, we want to put it all together and add the missing components in order to actually analyze a complete sound. So we start from a signal of X, and then we do the standard windowing, FFT, and these are the things that we talk about in this week. So the peak detection and how to get the amplitude, frequency, and phases of the peaks. Then today we're going to talk about the sinusoidal tracking, so how to build tracks out of those peaks. Then once we have these sinusoidal tracks, we can do the synthesis. So we can synthesize the spectral peaks, or the shape of the sinusoids in the spectral domain. And then we can do the inverse FFT and do the overlap add, so that we sort of add the time varying aspect of the sound, and we can reconstruct very complex sounds. Let's open up the file that includes most of the functions that are needed in the sinusoidal analysis, which is the sineModel.py, which is part of the SMS tools package. In this file, we have several functions that are of use for the sinusoidal modeling. For example, this first one is the sinusoidal tracking. Then there is another one which is cleaning sine tracks that we will talk about. Then there is one that implements the whole sinusoidal model, analysis and synthesis, but does not include the tracking aspect, because this is meant to be used in real time. So it cannot do tracking and allow some memory in the process. So we do not recommend to use that unless you want to develop some real-time kind of concept. So what we're going to be using and we recommend to use is the sinusoidal sineModel anal function that just performs the analysis part and is able to do sinusoidal tracking, because it allows to have all the tracks in one place and then do some post-processing of them. Okay, so in here the input is the whole input sound X, the sampling rate, the window, the FFT size, the hop size, then the threshold for the peak detection, and then a number of parameters that are important to control the kind of these time varying aspects of the sinusoidal tracking. So for example, one is the maximum number of sines that will be allowed at the same time. Default is 100, so normally you put quite a lot of them, so to allow for creating and disappearing sine waves. And then we control the minimum duration of a track, so the default is 0.01, so the tracks that are going to be shorter than this value are going to be deleted. And then we're going to control the allowed deviation from one frame to the next of a given track. So in this case, this deviation, which is in hertz, 20 hertz, it means that in the lowest frequency, it allows from one frame to the next for a peak to change a frequency by 20 hertz and still be part of the same track. And then this depth slope is a way to allow for this deviation to increase as the frequencies are higher. In higher frequencies, normally you would like this deviation to get higher, so we can change that by controlling the slope. The bigger this, the bigger the slope, and therefore the bigger the change with the higher frequencies will be. Okay, and then in the function, it's not that long. Of course, it has a lot of the parameters and the functions that we already have seen. The core is this while loop that basically what it does is iterates over the whole sound, and it performs all the blocks that we talked about. So it performs the DFT using the FFT algorithm, it performs the peak detection, then it performs the peak interpolation, and then it puts these peaks into tracks, and this is what we're talking about now. So let's look into this function, the sinusoidal tracks, which is right here. Okay, in this function, from the peaks that the algorithm has found in a particular frame, and from the concept of tracks, the concept of a series of incoming tracks with specific frequencies, we are building tracks. We are basically continuing the incoming tracks or creating new tracks according to these deviation parameters. So this function is a little bit long, but it's a lot of cleaning and setting up things. The whole concept is not that complicated. It's simply the idea that if there is incoming tracks, and if not, tracks will be created, but from these incoming tracks, it finds the peaks that are closest to those tracks. And then if it's close enough, according to deviation, they will become part of the track. Okay, so if this deviation is small, we will add it. And otherwise, we can also create new tracks here. Okay, so if there are peaks that are left that have not been assigned to any existing track, we can create new tracks. So tracks will be created and will be disappearing if they are not used in the following frame. Okay, so this returns a series of tracks. Okay, so if we go back to the function of the sineModel anal, okay, after this tracking, it's done. Well, again, there is a whole bunch of variables needed to handle these tracks and how to pack them in and clean the matrices so that we save space. But then this is done until then, and then once everything is done, before returning the tracks, there is a cleaning step. So this cleaning step receives all the tracks that have been computed for the whole sound, and it will delete the ones that are shorter than what we specify. So if we go to this function, the cleaning of the tracks, cleaning sine tracks, it's a very simple. It just simply goes through all the tracks that have been created. It looks for the beginning and endings of each track fragment, let's say, and if a track fragment is below a given length, then it will simply delete the track. It will set the frequencies to 0. And that's what it means to clean the tracks. Okay, and that's all the sinusoidal model does, the analysis of that. So let's use a function that or a script that calls the sinusoidal model anal. Okay, so this is a script that calls the sinusoidal model anal and with a given set of parameters, with a sound, the oboe sound, with a given window, given FFT size, etc. All the parameters that we talked about. So let's run this function or this script, and well, it will print the actual tracks. Let's run this then. Run test 6. Okay, so this of course will take a little bit more than a single short time Fourier transform. So this is the result. Here we have all the tracks, and we see the tracks in different colors. And things that are important to notice here is that, for example, even if we see a single line, we can see that there are several colors. That means that a track was alive for some time, and then it disappeared. So a new track started, and then it disappeared. A new track started and disappeared, etc., etc. So this is the idea that tracks can appear and disappear. Then also we see that most of the tracks correspond to the harmonics of the sound, but some do not. For example, here in the high frequencies, clearly we see tracks that are quite short-lived, and they may be tracking some noise component, or they may be tracking some side lobe of the analysis. And this is something that with the sineModel we cannot do anything about it. Of course, we can control the length. So all these tracks, the minimum length was the one that we established, which was 0.1 seconds. So all the tracks here at least are 0.1 seconds. If we had set this up to a different value, for example, let's leave it to 0.0. So, and now we can run it again. It will do the same analysis, but it will allow to do many more tracks. So now, well, it track things higher up, but if we zoom into the area we were looking at, yeah, we see many tracks that are very short and presumably correspond to fragments of little sounds or side lobes or things like that. So the cleaning of the tracks is a good way to get rid of all these kind of that typically may be corresponding to artifacts. Okay, then we can do the synthesis. So the sineModel synthesis is this function here, and it will receive these tracks that we analyze, and from them it will call basically the generation of the spectral signs. So it will iterate over all of them, and it will generate the main lobes of the Blackman-Harris windows. Here there is some consideration for the phase. We might want to not pass any phase. Here it passes the analysis phase, but in some cases the phases will be reconstructed from scratch, and it allows for reconstruction of the phase at the synthesis stage. Anyway, so this sineModel function, which is in the actual function that is called by the interface that we use in the demo class, it has one function, main, that calls the analysis and synthesis of a given sound using this sinusoidal model. So the parameters, the default parameters, it uses this bendier sound, and then it does the analysis and then performs the synthesis, and it outputs the sound file. And it also plots the input sound, the sinusoidal tracks, and the output sound. So let's just call this function. Let's close this one first. And if we run sineModel function, so we copied in our directory, and we had to change a few of the relative paths of files. Okay, so now it's computing the analysis and synthesis of this bendier sound. Okay, so this is the original sound, and here we see these trajectories and the resynthesis from that. So if we zoom into here, for example, let's zoom into a particular area, we will see all these quite messy sinusoids that are coming in and out. And in this type of sound, that's quite normal, because there is a lot of very partials that are very unstable, and they disappear and appear in a short fragment. Okay, so we can listen to those sounds. For example, let's listen to the resulting sound. So we created a file in this directory, the synthesizer is called bendier sineModel. So we can use the play system command to play this sound. Okay, and it's not that different from the original file that the bendier we inputted. So anyway, so that's that gives you an idea of how to use the SMS tools code and how to understand it. Now the idea is that by yourself you can play around with these parameters and really go into the different functions and understand what they do. So let's finish with that. And so we have seen the whole sinusoidal model from a programming perspective. And within the SMS tools package, we have seen all the functions that perform all these different analysis tasks and synthesis tasks. So we have a pretty good code base with which we can do a lot of very interesting things. Again, this is just one step into further complications on these models. So now we have seen the sinusoidal model as a model that will allow us to do quite a few things, but we can do more. And so next week we will be talking about the harmonic model, which is a way to restrict the sinusoidal model to track only the harmonics, like in the oboe sound. I think it was clear that it made sense to do that. And we will also extend it with other new approaches to the spectral analysis and synthesis sound. So I hope to see you next week, and thank you for your attention.